Welcome to The Explainer. Today, we are cracking open a true classic of the field, Chapter 1 of Asher Paris's Quantum Theory. We're going to deconstruct the absolutely massive shift in thinking that happened when we moved from the neat, predictable, clockwork universe of classical physics to the strange and wonderful, probabilistic world of quantum mechanics.
You know, for centuries, the whole foundation of physics was built on this really comforting idea called determinism. The universe was basically seen as this giant, intricate clock, and the thinking was if you could just know the exact position and momentum of every single gear, every little piece, well, in theory, you could predict the entire future with absolute, perfect certainty.
So, the classical illusion. And we're asking, why did our common sense view of the world have to fall? Well, the thing is, that beautiful, predictable clockwork universe, it was all an illusion. And that illusion completely shattered the second we developed experiments that could peek at the world one tiny piece at a time. Okay, so let's really break down the difference here. On the left, you've got the classical world, and it really rests on two, seemingly common sense beliefs. First, that objects have definite properties, think position, momentum, whatever, even when we're not looking at them. They just exist. And second, if you run the exact same experiment twice, you're going to get the exact same result, every single time. But then, you look at the quantum reality on the right, and it basically throws both of those core ideas right out the window.
Section 2. The Rise of Randomness. We're going to see how a simple experiment with light just completely broke determinism. So, what was the experiment that shattered this entire classical worldview? You might think it was something incredibly complicated, right? Like a huge particle accelerator. But no. It was actually a surprisingly elegant and simple experiment, and it all started with just a beam of light.
All right, let's walk through this classic experiment step by step. So what you do is you shine a beam of polarized light and you pass it through a special type of crystal, something like calcite. Now this crystal is birefringent, which is just a fancy way of saying it splits the light beam in two. And what you see on the screen at the end are two distinct spots of light. Now here's the thing, classical wave theory explains this perfectly, no problem. It can predict exactly how bright each of those spots will be depending on how you rotate that first polarizer. So far, so good, right? Everything seems perfectly predictable.
But this is where things get really weird. What happens if we turn the light way down so that only one single particle of light, one photon, goes through the setup at a time? Well, that's when determinism completely breaks down. For any individual photon, we have absolutely no way to predict where it's going to go. Will it hit the top spot or the bottom one? It's totally random.
Now, here's the kicker. Even though we can't predict any single photon's path, we can predict the overall statistics with mind-boggling precision. It turns out the probabilities follow this exact mathematical rule, which depends on the angle of our polarizer, alpha. And this is so important. This wasn't happening because our instruments weren't good enough, or because we were missing some kind of hidden information. No, this was a new, fundamental truth about the universe. Randomness is literally baked into the fabric of reality itself.
All right, next up, speaking a new language. Because if the old concepts fail, you're going to need new words. You see, this discovery of built-in randomness meant that the old language of physics was suddenly obsolete. Words like objective properties, the idea that a photon just has a certain polarization, that language was now completely useless. To even begin to describe what was actually happening in the lab, physicists needed a whole new, much more precise vocabulary.
So the first new term is preparation, and it is pretty much exactly what it sounds like. I love how Asher Perez puts it. He calls it a recipe in a good cookbook. It's the complete, totally specified procedure for everything you do to set up the system before you even think about getting a result. So going back to our light experiment, the preparation is all the stuff you do at the start, setting up the light source and adjusting that first polarizer. That's your recipe.
Okay, and the second new term is test. So if the preparation is the recipe, the test is the part of the experiment that actually asks a question and, crucially, gives you an outcome. It provides a new piece of information to you, the observer. So in our experiment, the calcite crystal and the detectors that tell you which spot the photon hit, that is the test. So think of it this way. Preparation sets the stage, and the test is the action that produces the final result.
And this brings us to an absolutely critical point. A direct quote from Perez himself, the question, what is the polarization of that photon, cannot be answered and has no meaning. Think about that for a second. This new language forces us to completely abandon questions about what properties a particle has. That question is now meaningless. The only question that makes any sense to ask is, okay, if I perform this exact test, what are the odds that I'm going to get this specific result? It's a total shift in what a valid scientific question even is.
Okay, section 3. What is a measurement? This is really the final and most profound shift in thinking. So let's see how all these pieces, randomness, preparation, tests, how they all build up to a conclusion that completely redefines the very idea of what a measurement even is.
And there's another classic experiment that illustrates this point just brilliantly, the Stern-Gerlach experiment. Here's the gist. You send a beam of silver atoms through a specially shaped magnetic field. Now, you might expect them to just spread out on the screen at the end, but they don't. They're deflected into two and only two distinct spots. And what this tells us is that their internal magnetic moment is quantized. It can only take on one of two possible values. For simplicity, let's just call them up or down.
Now, classically, your intuition would tell you that this magnetic moment is just like a tiny arrow, a vector, pointing in some fixed direction in space. Simple enough, right? So, let's push that idea. What do you think would happen if we set up 3 different possible tests, orienting our magnet along 3 different axes that form a perfect triangle, each 120 degrees apart from the others?
This leads to a massive contradiction. You see, basic geometry tells us that if you take any vector and measure its components along those 3 symmetric axes, the 3 results you get have to add up to 0. It's a mathematical fact. But, and this is a huge but, the experiment has already shown us that the result of any single test can only be plus mu or minus mu. There is just no way to pick 3 numbers that are either plus mu or minus mu and have them sum to 0. It's mathematically impossible. A total contradiction.
So what on earth does this contradiction mean? Well, it forces us to accept an absolutely incredible conclusion. The value of the magnetic moment that you measured, it simply did not exist before you performed the test. The atom didn't have a pre-existing up or down property that was just waiting for you to discover it. The very act of choosing how to set up your test, the very question you decide to ask, is an active participant in creating the result you get.
And this brings us full circle to a final, profound thought from Paris, which really sums it all up. A measurement is not a passive acquisition of knowledge. It is an active process. We aren't just detached, passive observers of the universe. We're in an active dialogue with it. The questions we choose to ask literally help shape the answers that reality gives back to us. So that clockwork universe we started with? It's not a clock we're just watching from a distance. Every single time we look at it, we are helping to set its hands.